Good. So this is a lecture that I give quite a lot. I don't know how familiar you are with the topics that we're going to discuss today, but I'm part of a minority here in Hong Kong and HKU to talk about challenges in science. So I'm going to be very frank and open with you. Some people say perhaps we shouldn't be talking to students about this. Maybe we should wait until they graduate or until they come back in a master's, or until they do a PhD. But I feel it's very important for us to be as transparent and as open as possible about all the challenges that are happening right now in science. This is especially important because of the things that are happening right now around the world, where there's a big clash, political views kind of intercept everything that's happening with science. There's a big problem with misinformation and disinformation. And sometimes not being transparent about what's happening in science is giving a lot of fuel for the people who try to cast doubt on science. And we've seen a little bit of that happening during the pandemic, where there was a lot of confusion. Should we be wearing masks? Should we get vaccinated? Should we do this? Should we do that? And because the information from science kept updating, we were all very, very confused. And I'm not talking about students. I'm not talking about laypersons in the street. I'm talking professors and people who do academic research are very, very confused about a lot of things. You need to have a comprehensive understanding of what science is in order for you to be able to evaluate the credibility of science. Okay? I'm going to try and walk you through some of the challenges of what has been happening in social psychology as a lens for the other sciences, but I'm going to touch on other fields as well, like cancer biology. So first of all, we need to agree on something very important, and that is that we need science in order to better the world. We have all these challenges. We have climate change happening. We had a pandemic not too long ago, of the age of AI, misinformation, disinformation. So all of these things we need to address in some kind of way. And right now, the best tool that we have, even if it has some weaknesses, is science. Science allows us to progress. We'll talk about, in one of the sessions, we'll talk about the advancements of humanity, is human nature good or bad, and what has happened. How do we know whether the world is getting better or is it getting worse? But generally, science is needed for that. And not just any science, we need science that we can verify, science that is credible. Hopefully, science that is optimized. So if we have a pandemic, that we're able to very quickly address this pandemic without millions of people dying for a long period of time. So my question to you, something that you should think about. We're not going to open this up for discussion because I want to give you like a general perspective. But before I show you this thing, take a moment to think. How do you think science is doing? You're here at HKU studying what we refer to as psychological science. Everything that we do, we try to help patients, we try to help education, try to do all kinds of different things. And we try to leverage scientific insights. So it's good to take a moment, sit down with ourselves and think, okay, so if we read an article, I go on Google Scholar, I search for something, an article comes up and it says all kinds of things in abstract. Is this credible or not credible? How do I know that it's credible? All kinds of people have different ways to evaluate this. Some people say, oh, I only believe things that come from this journal. Some people say, oh, I only believe stuff that comes from HKU. And we'll have some kind of other measures of how they determine on Google Scholar what kind of article is credible or not credible. But I have to say that for me, for a very long time, even though they taught me how to use Google Scholar, how to read an article and look at the abstract and look at the methods and look at the introduction, I still didn't know how to evaluate whether something is credible or not credible. So take a moment, think for yourself, how is science doing? Is it doing good, not good? What are the weaknesses? How can we improve? All right. So I'm going to start with a project. And this project has been going on for 10 years. It was published around 3 years ago. And this is a project from preclinical cancer biology. So we're not even talking like social psychology or psychology in general. And what they did over here is they tried to design 193 experiments that would repeat classic findings in preclinical cancer biology. So it means that you look at the entire literature and you say, I want to know how to treat cancer. I want to know what works and what doesn't work. And you can replace cancer biology with anything else. You want to know whether vaccinations work. You want to know whether something in psychology, a treatment therapy works. CBT works, doesn't work. An educational program works or doesn't work. How do we know this? So they said, we just want to revisit the classic finding. We're going to find the biggest article, and we're going to try and see whether these are credible or not credible. How do we establish whether these are credible or not credible? We have two main things that are very important in science. One is reproducibility. Reproducibility means that if you read the article, you know exactly what it is that they did. And if you take exactly the same data from them and you run this again with an analysis, that you get the same kind of result. Already here, we have a problem. What is the problem? You don't need to be in cancer biology in order to understand this problem. Even as students, as scholars, I want to understand something that has been done in neuroscience, in clinical psychology, in social psychology. I go up, Google Scholar, take down the article, and I try to read it. Do I really understand what they did? Usually the answer is, I don't. Why don't I? Because the method section is very, very short. It's summarized. It doesn't give you all the materials. It doesn't give you all the scales. It doesn't give you all the interventions. You don't know step by step, what did they do? At what point in time? How did they execute this? Using what programs? What were the conditions of the room? Who are the participants? You have a lot of details there that you actually know nothing about. In clinical cancer biology, it's even worse than this because a lot of these are lab experiments. And they involve a lot more than just setting stuff up on a survey, on qual checks. It means that there is a lab, there's a whole procedure, and you need to time things very, very carefully. And if you don't know how to follow this, you're completely lost and you might get different results. And the amazing thing is, they were aiming to reproduce and then replicate, but first reproduce 193 experiments. But very fast, they came to the conclusion, we can't do this because we actually don't know what happened there. So what did they do? They reach out to the original authors and say, we want to reproduce, we want to understand what it is that you've done here. And the reactions that they got from the researchers were very disappointing. First, many people don't reply. Many they died, maybe they left academia, they went to industry, maybe they just don't like to answer the email. But then even if they answer, we get some replies from them that are very confusing. Some of them refuse to share what it is that they've done. Some of them claim all kinds of things that I usually hear from students. It's like, I lost my laptop, I have this problem, I need positions, I can't find the documents, I don't know. So they started from 193, but actually the experiments that they conducted, only 87. Well, this is already a big problem with reproducibility. More than half, they were not able to understand what happened then. And we're not talking about other people just trying to understand from the street or experts in the industry. We're talking about academics reaching out to other academics and trying to understand academic articles. So 193 to 87. But at the end, they were only able to complete 50 of those. So even from 87 to 50 is a big drop. And why is that? Because when they started doing the experiment, they realized that they're missing a lot of information. And that information, the original authors were not able to complete. So this is already a big shock for us, and this took a very big effort. And one of the problems in science is that we actually don't do this a lot. This is very unusual. Usually we don't go and revisit some of the findings. We just take them for granted. Somebody did something in the 1970s on a sample in Princeton of 20 students, and then forever we do TED Talks, we publish books on this, and we just say, yeah, this is scientific. This is the truth. Nobody tries to run this again. So whenever I say something to you about something that took place, I try to show you evidence that happened again and again with replications, with reproductions. So this is already showing a problem. People usually don't do reproductions, and when they try to do reproductions about something very important like cancer, they can't do this because only 50 out of 193. This is a very low percentage, a very low ratio. Okay, let's say that we understand that this is a problem in reproducibility and we're going to work on it. How about replication? So what is a replication? A replication is if I know all the procedure and I run the same kind of thing again, am I going to get exactly the same result? Turns out that this is also a big problem. So here we have what is the percentage of positive results, so showing exactly the same results as in the original. So out of the 23 papers, two out of the 23 papers. How about the experiment? 2 out of the 50 experiments, 6% of replication, successful replication. Then we have effects, 13%. Out of all the outcomes, 18%. So out of the 50 that they were able to start, how many of the things were able to replicate successfully? Very low percentage. This is a big shock to us. Because we understand that actually if we read something that articles wrote about cancer biology in some of the top journals, and we try to run exactly the same thing again, then we realize that we can't find these things. What to do about this? It's a big question. Now, the way that we evaluate usually whether we find support or don't find support for an effect is something called p-value. It's a very elusive thing. I don't know if you completely understand what a p-value is. It took me a very long time. I finished a complete PhD without knowing exactly what a p-value is. Only doing my postdoc, I sat down in a room full of people, experts, professors, and somebody asked, the person who gave the workshop, asked people, what do you think a p-value is? And then we went around the room. We saw that everybody had their own description of what a p-value is, and everybody was wrong, including myself. And only then I realized what a p-value actually is. But let's say p-value, we understand we need to look for p-value lower than 0.05. We don't know why, but somebody told us that this is what we need to do. Here you can see the distribution of the original and some of the replication. So you can see the original findings, all of them are p-value lower than 0.05. How about the p-values for everything else? You can see just distributed everywhere, lower than 0.05, higher, it's like all over the place. So original finding compared to replication. Very disappointing. So it's not just that it didn't work, it didn't replicate just a little bit more, maybe the effect was just a little bit weaker. It was all over the place. We don't know why this is happening. So here are some of the summaries. This is somebody from Twitter. He's what's referred to as an open science guy. So I consider myself to be part of what's called an open science movement. This guy fights publishers. We'll get to the problem of publishers. And this is how he summarized this. 2013, let's replicate 193. Okay, we can't do this, so let's just start from 50. Okay, we can only do like 18 of them, and then out of those, how much is the full replication? Very low rate, 10%. Very, very disappointing. So you might think, okay, maybe something is very wrong in cancer biology. Maybe they picked the wrong studies. Maybe something is specific about this. And I'm here to tell you that this is actually reflective of a much bigger problem in science. And the immediate question that you might have in your mind is, how big are these problems? And I'm here to tell you that it's very important that we communicate to you, students, especially where you are right now. So you're about to graduate, you're about to finish your studies, you're doing a thesis, you're doing an internship, you're doing a lot of important things right now towards the end of your graduation. So you need to know about these problems. How big are they? So I think these are very, very big problems. It's very important that we talk about these problems, okay? So I have to say, sometimes people just want to push things aside. So I collect these things. It's my hobby. I read a lot of newspapers and I track science, and I want to show you that this is not just a problem in cancer biology. It's not just a problem in psychology. It's a problem that's all over the sciences. So here are some of the headlines. It's not limited to psychology. In medicine, stop working. Reproducibility in chemical research. Economics has a problem. Even computer science, you would expect things that are closer to math or physics. Got here, quantum computing. And this is the latest one, like cancer research is broken. 2015, after the big shock from the science paper, a lot of people took this into heart and then started what is called now the science reform movement, the open science people who want to open everything up. We want open peer review, we want open materials, we want open data in the code. One of those advocates is a person called Chris Chambers. He wrote this paper. He wrote the 7 deadly sins of psychology, because back then we really thought that this is psychology. But since then, we now know that all these sins are not the sins of psychology. These are the sins of science. And what are these sins? Outcome bias, confirmation bias, publication bias, hindsight bias. When we see the results and we don't like the results, then we just reject them. Let's say now I'm in a peer review, I was a peer reviewer, and then I saw the outcomes already, and I said, okay, I don't like this vaccination, came from whatever country, reject that paper, right? Another problem, big problem, is the publication bias. Let's say, for example, there's a vaccination and there's 100 studies conducted that showed, we're trying to get to show that the vaccination has an effect, but out of the 100, only 2 work. If I submit all of this to journal, what ends up happening is for 98 of them that didn't work, the journal say, this is not interesting, this is not counterintuitive, this is not novel, this is no findings, you didn't find anything, reject. What ends up being published? The 2 that did work. But if you don't publish everything, it seems like, oh, 2 out of the 2 work, therefore vaccination works. But if you don't publish all the 98, then you don't know that it's actually 2 out of the 100. The publication bias is a very big problem. This is why meta-analysis, which we will discuss, they always have to come with a publication bias assessment and possible adjustment. So we need to see everything that's published and not published. As long as the publication relies on p-value lower than 0.05, a big problem, because we don't see all the things that don't work. And that's why if preclinical cancer biology doesn't replicate, it could very well be that one person found this, but just because of the randomness of the universe, they found p-value lower than 0.05. But 99 others tried to run exactly the same thing, but didn't find anything. But they don't publish this, because if we submit it to the journal say reject. And then at some point we realize, oh, we're going to reject this anymore. We're not going to submit anymore. Publication bias is a big problem. So very good. And we're going to discuss some of these things. In addition, you see the life cycle. We realize that the life cycle of research, in every step of the way, we have problems. First problem that we have, we just don't run any replication. So you can see the first finding. In 2012, they were trying to understand, why are these things happening? So we just need to do more replications. How many replications did we actually do? And they found out that out of 1,000 articles published in journals, only 1 out of the 1,000 are replications. And even then, it's not necessarily a direct replication. That could be a conceptual replication, but it's not as close. So we just don't repeat things. We just want this obsession with novelty, keep novel, counterintuitive, oh, the top journals. And then we have all kinds of other problems, like the lack of power, just like I told you with candidate A and candidate B. People are just running a lot of things with very, very low samples, and then they're not replicable. They have low power. And then we have something called questionable research practices, and I'm going to show you what questionable research practices are and why they're so bad. So now we understand that between 50 to 100% of people up until 2012 were doing something that we now consider to be questionable research practices. And then we have all sorts of things like harking, hypothesizing after the results are known. I hypothesized that this, but then what I found is not this. I found something else. And I said, oh, no, actually, what I hypothesized was not this. It was this. And then I changed the hypothesis to meet the outcome. This is harking, hypothesizing after the results are known. That's not hypothesizing. That's just changing the story of how you came to the conclusion that you came. So all these things are very, very problematic. Any questions so far about everything that we've been talking about? So the findings, at least for social psychology, as my summary is that the findings that were p-value lower than 0.05 in the top journals have 30 to 50% of them replicate, and with the impact of about half of what was originally published. That's a general estimate for that. But we need to find out, and this is the tricky part, and this is why the first task that we have is so complicated. We need to understand, if we see a literature, what can indicate that this is of higher credibility? How can we take out the ones that are lower credibility? How do we identify them? But first, we need to understand not 100% of what we read on Google Scholar is credible. Then we need to come out with a way for establishing what is reliable and what is not. So that it's not 50-50, it's not 70-30, but it increases the chances of us looking at something that is credible. So for example, if we see many replications of something over time, and these are done in a certain way, and we're going to talk about pre-registration and a register report, and if it has open science, has open materials, data, and code, if we have all of these measures, then we have higher ability to conclude that this is more credible than others. But right now, we just need to understand that the status quo of science, the way that it is, closed science, we don't see anything. The trust system rather than an ability to really evaluate the credibility of that science. So a very curious case study. And I remember this because this was kind of like the middle of my PhD. And we couldn't figure this one out. We couldn't understand what's happening. So just so you understand, Journal of Personality and Social Psychology. In social psychology, this is one of the most reputable journals, high reputation journal out there. So if you publish in JPSP, it means that you're a very good scholar. Getting in there, I think it's like a 90 or 95% of rejection rate. So here we have a study that was published by a social psychologist from Cornell, Daryl Bem, showing many experiments. So you can see 9 experiments involving more than 1,000 participants, but it's trying to do something very peculiar. So typically, if you go to a psychology lab at HKU, many of them hook people up to all kinds of machines, put them in front of a screen, and show a lot of stimuli. And then they measure what happens. So for example, heartbeat, sweat, EEG. Sometimes they put you in an MRI, something like, in order to see what's happening to you, the kind of reactions that you have. And different stimuli elicits different things. So we can sometimes see the brain, or we can see the sweat. And to get the strongest reaction, typically we use very strong stimuli. It could be something that's horrifying. Here, for example, one of the things that we use is erotic stimuli, so pornography. It seems like these things really activate everything in us. So what Daryl Bem was trying to do is to say, instead of first I show the stimuli, and then I measure what the response is, I'm going to do something opposite. First, I'm going to measure, then I'm going to show the stimuli. And then I want to show that people react to the stimuli in advance. So even though what is going to be presented is randomized, so they don't know if they're going to see something in pornography or horror, they have no idea what's coming next. Already before I show them the stimuli, the heart starts beating and I start to sweat and everything lights up. So he was trying to show something that physicists have been trying to test for a very long time. And across the different domains, there is an understanding that this is impossible. But Daryl Bem said, impossible, but I conducted all these experiments. 9 experiments, 1,000 people, I invested money in this, and then I was able to show statistically significant results for almost all of the studies, 8 out of the 9, all but 1. And then he submitted this to the journal, and the journal and the reviewers were very, very puzzled by this. So what do you usually do when you have this kind of finding? Usually you ask the person for the data and the code and everything like that. And usually the author said, no, I don't want to share. But in this case, he was willing to share. So he showed the data and the code. This is not fraud. He actually collected this data. The data is real. He did not play around with this data. The data seems to really indicate that this is really what he found. So something is very, very fishy about what's going on here. And it's not because of fraud. So finally, the editor made a very difficult decision of saying, we can't find anything wrong with this in our peer review. Therefore, I'm going to publish this. And when he published it, all hell broke loose. We were just horrified by this because it's obvious But if you're able to find evidence for that, you might be able to find evidence for anything. Now, the question is, when this kind of thing comes out, how do we know whether this is credible or not? If you look it up, right now it appears in Google Scholar, how do we know if this is true or not true? First, it's impossible. Right? And if this is possible, this is definitely not the way to look at this. You have a lot of physicists that can do a lot more in order to test it. But what does this mean? What can we do? So one of the first things that we said, and this is why up until 2011, we don't have any replications, but in 2011, we started to do replications. We said, oh my gosh, we're able to show in psychology that people can predict the future. Let's just replicate this again. So other labs, for example, Stuart Ritchie over here, was a student back then. He just said, okay, I want to do this. I want to predict the future. I want to know what's happening. He tried to run this again 3 times. It was unsuccessful. So finally, he wrote this up and he submitted this to JPSP, the same journal. What did JPSP say? We are not the journal of failed replications of BEM. Reject. So the only journal that was willing to publish this is a new journal. Today, it's a very reputable journal that promotes open science, PLOS1. Not for profit, it's a non-profit, PLOS1. And they say, we care about the credibility of the evidence, we don't care about the contribution, we don't care if this is novel or not novel. So they published this. And this got everybody talking about that. So there was a big backlash against JPSP. And finally, JPSP published another failed replication by this group, correcting the past failure to replicate site. If you go and look at the citation rate for BEM compared to the replications, which ones get more citations? BEM does. They'll get citations. Even though we corrected this, correcting in the future, we did not correct it because it still goes on Google Scholar and has not been retracted. It's still out there, and people still think that they can predict the future. And if they run the same thing again, they're going to waste taxpayers' money and try to find it. And again, we have more and more that shows that this is just impossible. I don't know why, but up until now, 13 years later, people still conduct replications of this and fail to find these effects. If you want to read about this, Stuart Ritchie came out with a book called Science Fiction. He decided to quit academia, even though he was a very prolific researcher, and he's now a podcaster. And he has a very, very good podcast about trying to assess what is credible and what is not credible. And I encourage you to go and listen to Stuart Ritchie, because he really knows this stuff. So there's 2 people over there that talk about these things. When a finding comes out, how do we know whether this is credible or not? When you listen to a TED Talk, how do you know that what the person is saying, aside from the 50 million views, how do you know which claim is true or not true? So he took it upon himself to try to communicate to the masses that there is a problem in science and how to overcome it. This came out 2015. I remember this coming out because this was a very big finding. And occasionally when you open the media, especially if you go through the TikTok, the Instagrams and all this, occasionally you've got all these influencers saying, oh, there's a new study that said that. You know, if you eat chocolate, it can help you lose weight. So this is great news because we don't need to watch our diet. We don't need to go and exercise in the gym. All we need to do if we want to lose some weight is just eat more chocolate. And the media loved it. Back then, there were no influencers and no TikToks and Instagram. We just had the traditional media, so you can see the Huffington Post and all that. As the world gone cocoa, eating chocolate can help you lose weight. And this, again, is not fraud. This was actually a real study that was conducted. And then you want to ask questions, what is it about the study that could have led to this result? Luckily for us, and this is what's great about this case study, is that the person who conducted the study actually shared how he did this. I fooled millions into thinking chocolate helps weight loss. Here's how. Here is a dirty little science secret. So this is a secret we all want to know because we want to publish in top-tier journals. If you measure a large number of things about a small number of people, you are almost guaranteed to get a statistically significant result. How did they do this? Our study included 18 different measurements. They didn't report all the 18 in just one of them because of the randomness of the universe, because of the way p-values are. One of them worked, but they measure all these things, not just weight, but cholesterol, sodium, blood protein, sleep quality, well-being. And only this is from 15 participants. So that means a very small sample means very large error. So there's more, if you measure many, there's more chances of you finding something that is not real. This is what error means. And you can capitalize on error because as you measure them more, then one of them is going to show up as significant. Just so happens that it's the funky one, weight, right? Not only this, but one subject was dropped. So after looking at the results, they're not p-value lower than 0.05. They're just above, so 0.07. And they say, oh, I remember. That participant was sick that day. I'm just going to take him out. And then I'm going to say, okay, I found some reason why this participant should not be included. That study design is a recipe for false positives. You might look at this and laugh, but I did a PhD from 2009 to 2014. And I can tell you, Many of these things were common practice. Not disclosing all your dependent variables is common practice. Excluding outliers after looking at the data was common practice. A lot of these things was common practice. Could be that maybe Ben did some of these things in the 9 experiments. So how do we know that people were doing this? So for example, Barry Ben actually wrote a book giving advice to students on how to do your article. There are 2 possible articles you can write. The article you plan to write when you design your study, which is how we think of science, or the article that makes the most sense now that you've seen the results. Then you look at the results, you say, oh, maybe I found this, I didn't find this, maybe I exclude that, maybe I only focus on this DV. And then say they're really the same and the correct answer is B. This is the advice, and many people follow this advice, but I can tell you the correct answer is definitely not B. B causes a lot of problems. And for him to give this kind of advice just shows how bad these things are. And not just back then, but also more recently, people from Harvard, 2019, this kind of advice. In presenting a result, you have to tell the truth and nothing but the truth. Oh, great. Sounds amazing. What you don't have to tell is the whole truth. What? But what happens if I ran some randomized control trials on a vaccination and they didn't come out? What do I do then? I just throw them to the foul jar? No, it's my obligation to share everything, things that worked and things that didn't work. Right? So to tell the whole truth, in other words, you can select the results that you present. You need to create a story. The problem is that the story is not completely aligned with scientific truth. So in open science movement, science reform people saying we need to share everything, we need to show everything. We need to show the good and the bad and the complexity, because otherwise we don't have a complete understanding of what's happening over there. Another case study, priming. This is a seminal paper cited by 2,463. This is actually somebody who back then was in UIUC, in Urbana-Champaign. Actually spent most of his time here in Hong Kong. So I remember I did my PhD at HKUST in the management department. He was in the marketing department. And I remember him. He's a great guy. Him and his wife were in the marketing department. And they were doing some really great research. And one of the things we were really proud that Bob Wire came to Hong Kong to be here with us and establish a strong community of research. And one of the big findings that they had from 1979 was that you can prime things, you can activate mindsets. If you activate mindsets like hostility, then it has all kinds of outcomes on the way people behave. So you can see that this came out. You can see just how much of an impact this is. We're talking thousands of articles. This is a very big literature. Here we can see this about hostility, but people have done this again and again. One of the famous studies by John Barge is that if you activate elderly mindset, if you activate words that have to do something with age, then people walk slower from the lab to the elevator. Big finding in the 1996. John Barge. This started a whole thing called social priming. Every year, when I'm a second examiner, I see at least one undergraduate student investing a whole year trying to do their thesis or their internship on social priming. Now, there is something very solid about priming, cognitive priming. When you do reaction tasks, you hit, miss, how much time it takes you to respond to a certain stimuli. But this is not that. What this one does is social priming, and what this does is unscramble sentences, having all kinds of different words, and then affecting behavior much later down the road. So this 1979, will this replicate or not? Here you can see a mass replication. And once we understood in 2015, because of the science paper, we understood that we need to do a lot of replication. This is one of the main papers that we wanted to try out. And this is what we did over here. So you can see just how many people were involved in this. And I know many of them. Randy over here took it upon himself to coordinate something that up until the 2015, we didn't know how to do. We didn't know how in psychology to collaborate everybody together. So they tried to repeat again and again this one experiment. But can you imagine just how much effort there is? Think of all the salaries, think of all the participants you have to pay for, think of all the time that was invested in this. What did they find? One of our seminal findings about priming, although the confidence interval for one outcome is still at 0 and the observed effect was in the predicted direction, these results suggest that the currently used methods do not produce priming effect that is practically and routinely detectable. This is a nice scientific way to say we couldn't find any support for this. And up until I remember doing my PhD, priming is what you did in order to get a job. This is in order to get published. This was the cool stuff to do. Now, we actually didn't need to wait until there's replication, because when we started looking at this article, we realized very, very fast that there is a problem. One example, when we look at the meta-analysis, you can see Sewell and Wire, 1979, on 80 participants, what is the Cohen's d? So we're talking about an effect size. So we have a tutorial on this, and I'm going to give you some tools in order to think about what is an effect size. But just so you understand, an effect size typically in social psychology, an effect size of 0.6 Cohen's d is considered strong. a Cohen's d of 5.65 is an impossible effect. There's absolutely no way that this is a reality. Why? Some people on Twitter, Randy in this case, the person who did this, that if you want to compare this, I don't know if you're familiar with this NBA guy, Shaquille O'Neal. Back in my days, he was the big NBA player. But this kind of effect is the difference between the average female and Shaquille O'Neal. So it's so noticeable. So just by activating some kind of mindset, this is the kind of behavioral effect that you get. Impossible. And what you all can also see that there's like this 80 participants back in 1979. Surely somebody has repeated this, but nobody has repeated it because there's no way to get anything published on this if it's just a replication. Right? Since we're talking about this, look at this meta-analysis. In this meta-analysis, you see that it contains a lot of studies, slow and wire, but then you've got stopple. Another thing that happened in 2011, I'm going to talk about this later in the semester, is that the Dean of Social Sciences in Tilburg University, Dietrich Stoppel, confessed after an investigation that everything he has ever published was fraud, manipulated, not real effects. Everything that was who was working with him was devastated by this. This is why, after 2011, the Netherlands decided they're going to clean up. So the Netherlands is leading open science in the world. When I say HPU is behind Europe, it's because places like the Netherlands and the European Union took it upon themselves to clean out and get rid of all the Dietrich Stoppels. But timing, they always say, you have thousands of articles on this. Let's look at the meta-analysis, Stoppel. All of these have been retracted already. So sometimes you read a meta-analysis, oh, they've done 100 studies, look at all this evidence. But then you look at each and every one of these studies, you see it's either text that cannot be real or something that was completely flawed and retracted. Need to be very careful with it. Not only this, but after we did this replication, we already understood that not only the effect size is unreasonable, but even when we look at this figure, so a four-way interaction among those variables was also significant, p-value lower than 0.02. With 80 participants, having this kind of clean figure is impossible. But nobody ever questioned this. It's been there in the literature since 1979 up until Randy did this in 2018. It's just unbelievable that this is real. So you can just look at this. And then we went back to Bob Wire and we said, hey, would it be that there's like an error here or something went wrong? And Bob Wire said, yeah, this probably is a mistake. This probably is a mistake? 2,300 citations. You know how many millions of dollars have been spent over this? For 50 years, we've been writing books about it, communicating TED Talks about it. Devastating, horrifying. So here you can see this is the way that we do meta-analysis and stuff. This is Sewell and Wire. Everything here in the dotted line is zero, a null effect. They showed an effect of this BV, effect size of 3.01, an impossible effect. All of the labs, the many labs from around the world, where are they? The confidence interval is overlapping with the null. It means p-value is not lower than 0.05. It means that they're aligned with the null. And here you can see the meta-analysis summary at the end, but this diamond here overlaps with the null, includes 0.00. Definitely nowhere close to Cohen's d of 3.01. You can see this for this DV and for this DV. It's a real problem. So definitely we can rule this out. Now you would think after so many labs and all these, we found problems and we found unreasonable effects, you would think that we would retract the original article, or we would make some corrections. But no, a lot of people fought back and said, all these open science people, horrible, replicators, they have an agenda. They want to take down the big professors. This is still not true. They have an agenda. Okay, what's the criticism? What is it that you criticize? No, you didn't work with us. If you only worked with us, if you only sat down with us in order to understand how we do priming, then you would find it. Unfortunately, poor Randy. After doing one mass replication project, he did this again in 2020. Again, look at all these labs. Just imagine how many people were involved, the salaries, the funding for this, all the participants. Why did they run this again? They ran this again because they wanted to address the problem that some of them did exact replication without the original authors, and the other ones did this with the original authors. And the hostile priming effect for both the close replication and the conceptual replication was exactly the same. We're not significantly different from zero. Despite our best effort to produce favorable conditions for the effect, we did not detect a hostile priming effect. So all these criticism coming out, this is really, it's so heartbreaking. I can't just tell you how many people were involved. There's a lot of people that I know have been doing priming. I'm familiar with most of these people here. And we were really hoping, maybe we missed something. Maybe we should just run this again and ask for their advice. And actually, if you look at this, the close replication and the conceptual replication, it's exactly the same effect. They contributed zero. After this, did everybody agree that, okay, now we don't need to talk about priming anymore? Because cognitive biases, because human nature, very, very difficult to let go of something that you've believed for a very, very long time. So for a very long time, we didn't detect the errors. Nobody ever looked at the statistics. Nobody ever looked at the figures. Nobody ever tried to replicate anything. Once we do this, we find some findings, and then somebody tells us, no, you need to collaborate with the original authors. Then we run this again, and we again don't find it. So just unbelievable to me that this is, when I came into a PhD, I really thought science would be completely, everything is clear, everything is taken for granted, everything works. It's not. Now it's up to me, a junior professor, and all these open science people, most of them are PhD students and postdocs, without tenure, without any funding. It's up to us to clean this literature. So a lot of case studies, I'm not going to go into all of them, but you can see all the replications that we try to do. All of them involved dozens of labs from around the world. People, open science advocates, trying to do commitment priming, honesty priming, death priming, embodiment, all kinds of things. All of these are failed replications. We just can't get priming to work. So social priming, please don't do your thesis on this. If you know somebody who's doing a thesis on this, please don't do this. And I urge you, before you do a thesis on anything, please check the literature and make sure that there's a replication, that there's a meta-analysis that does not include fraudulent studies, that the effect sizes are reasonable, that somebody that you know has an experience with this and can actually say for real that this has higher chances of replicating. Please avoid social priming. So does this mean that nobody's talking about social priming anymore? Of course not. John Barge, the guy with the elderly priming, still keeps doing talks and publishing books. New York Times bestseller keeps coming out of this. I really don't understand it. TED Talks, again and again. So very, very unfortunate. Now, I'm going to show you how could it be that there's 2,300 articles citing that showing an effect. We're going to do a simulation of what's now called questionable research practices, or p-hacking. Back when I was doing my PhD, this was common practice. In some of the fields, including fields here at HBU, including the field that I came from, I did not do my PhD in psychology, I did my PhD in a business school and management. Some of these practices are still happening. Even in our department, I see this again and again. And sometimes when I read a thesis by an undergraduate student, I see them doing this. So I want to show you what these practices are. I'm going to give you the tools to do these practices just so you know how bad these practices are. There are 4 different simulations. I'm not going to go into all of them. I have videos on all of them on YouTube if you want to go and watch. I'm going to show you one of them. Okay. All right. So let's do some p-hacking. And this is a very important tool for you to understand. So first of all, I want to say, I don't know what software you're using for statistical analysis, but I strongly recommend using R. And one of the nice things about using R, and now you've got like ChatGPT and Claude and Gemini, they just like write R code without any problem. But R is very, very powerful for many different reasons. One of the reasons that it produces this, you can very easily write something called a Shiny app, where you can allow others to run your code or run simulations or run things about your data without having to know anything about statistics. So creating this is actually very, very simple. So I just recommend that you get away from SPSS and you get away from all the other things and you just move to R. If you're using Jamovi, you're already halfway there because Jamovi is built on R. Not many people know this, but if you use the syntax, you have an option to show the R syntax and it will show you what it is that Jamovi exports, and you can copy paste the syntax from Jamovi to R. I'm going to show you this in one of the future sessions, but everything here is done with R Markdown and Shiny apps, okay? So we're going to p-hack. So we're going to have your favorite effect over here. So let's say, for example, I want to show that priming works. And then I'm going to use the number of participants. Let's say, for example, just like the priming effect, they had 20 in every condition. Now, I'm going to do a true effect of 0. True effect of 0 means that everything I'm going to simulate here does not have any effect, should not have any effect. If you're seeing any p-value lower than 0.05, it's just because of the randomness of the universe. It's not because there's an effect in there. Okay? I'm going to simulate a lot of studies and DVs that are not supposed to show any kind of an effect. How many DVs? We're just going to use as many DVs as we can, just like the chocolate study. So we're going to have a large number of DVs. And then we're going to run this experiment. We're going to see what happens, okay? All right, so if we look at this, what you can see here is that we have 40 participants, so 20 in each condition. And just because of the randomness of the universe, if I run this, none of this should be significant, right? Just, there's no effect there. It just simulated the junk noise, right? But you can already see the DV number 7, we already flagged this for us with a little bit of green, which shows that it gets very, very close to 0.05. So the p-value here is 0.085, okay? So when I see this, let's say I want to publish in Nature and Science, and I want to make something out of this data. I invested a lot of money in it. So I want to investigate DV number 7. So here you can already see like the plot. You can see the priming effect and you can see the control condition. And you look at this. And then after looking at the data, suddenly I remember that this participant over here was sick that day. So I'm just going to take this participant out. Okay. And then I go back to the DV number 7. And I see, oh, perfect. Now I have p-value lower than 0.05. So random data simulated has zero effect whatsoever just by me looking at the data. One questionable research practice is that looking at the data, then seeing the outcome, and then looking at one that didn't align with it, and then coming out with an excuse why to exclude this. Is this what Daryl Bem did? No, that's not what he did. So we're going to try and take a different angle to this. We're going to bring this one participant back, and instead we're going to do something different. We're going to go to this tab here on the left that's called Now p-hack. And now we can do a bunch of other things. We can add control variables, so covariates. We can control for age and gender, and any typical data set has a bunch of things. Are they local? Are they from Hong Kong, from mainland China? What the weather is, the cherry is brown or orange. It's like you can include whatever it is that you want. And the more covariates that you include, the higher the chances that the p-values are going to move up and down. And at some point, you're going to find something that you like. We're not going to do that. There's a different data set that does that a lot better. So I can show you that how Republicans and Democrats look at exactly the same data but have completely opposite conclusions. Here we're going to do something different. And this is called optional stopping. And this is likely what Daryl Bem was doing. So here you see add 5 participants, add 10 participants. So what I'm going to do is that I'm going to invite 10 more participants, random simulation, and then I'm going to peak. Invite 10, going to peak. And then I want to see what happens to the p-values. So please look at the p-values as I add participants, and you'll see something that we call the dance of the p-values. They go up, they go down. Randomness of the universe. So let's do this. I'm going to add 10. So I added 10 participants, PV number 7 disappeared. It's no longer green. It just shows how volatile this was, right? Randomness. I'm going to add 10 more. I'm going to add 10 more. I'm going to add 10 more. Add 10 more. Goes up, it goes down, and suddenly PV number 1 looks a little bit, maybe it's going in the right direction, lower than 0.1. And then I add 10 more, getting very, very close, 0.06. That's great. I'm adding 10 more. Now it disappeared. So you don't know what's going to happen. I'm adding 10 more, adding 10 more. And now I can see DV number 9 is showing some promise. I'm going to add a little bit more. Suddenly, just by the randomness of the universe, just by me peaking, adding 10 more, now suddenly I get DV number 9, show me lower than 0.05. I didn't do anything. I didn't exclude any outliers. I didn't do any. I just added more and more to them. And actually, you don't have to add 10 participants, but actually you can do this every time. So if you want to find p-value lower than 0.05, no problem. Just invite participants, peak. Invite a participant, peak. Every time you peak, because of the dance of the p-value, you increase your chances of finding a p-value lower than 0.05. Now, we know this now. We didn't know this in 2011. We didn't have this practice. But every time we peak, we need to adjust, compensate by adjusting the alpha. So you need to divide the alpha. So if the p-value that we aim for is 0.05, then if we peak once, then the p-value that we need to aim for is 0.025. If we peak again, divide by another 2, and so forth. But we didn't do this. Back then, you didn't have to. You could just peak as much as possible. If you peak for every participant, if you have 1,000 participants, then finally at the end, for each experiment, you can get yourself defined. Let's say, for example, that this is not good enough for me because I want to publish in Science and Nature. And Science and Nature require 2 dependent variables to be significant. So maybe I can keep going with this. I'll just keep going a little bit more. Add 10 more participants. Now we've got like number 5, and you can see overall, it's like this is getting close. So DV number 9 went down even further. So add 10 more. And suddenly also DV number 7. So now I have DV number 7 and DV number 9. So now I can publish in Science and Nature. Is this clear what I did here in the simulation? Any questions about this? This is what we refer to as p-hacking or questionable research practices. Okay? This can explain, together with publication bias, together with the incentives and the for-profit publishers, this helps explain why a lot of the findings are not as credible as we thought before. Okay? Now, a question that you might have, and this is very, very important because I do this with all my students, but I don't know that other professors are doing this. It's like, I want to do an internship or a thesis. I want to invest a whole year on a research idea. If it's a PhD, I want to invest 4 years on it. How do I know if something is credible or not? But I want to tell you, now we have the tools to see credibility. So I urge you, before you go and embark on doing a thesis or doing a study on something, that you use tools like the p-checker that I'm going to show you in order to analyze the literature, in order to see whether this is credible or not. So let's see what the p-checker does. This is another Shiny app. And what is nice about this, I don't know if you're familiar with StatCheck, but actually now, especially with the ChatGPTs and all this, you can upload a PDF and take out all of the statistics from the PDF. Automatically take them out. And then we can put them here. So for example, here on the left, you can see some of the statistics, the t-test and the chi-square and the correlations and the ANOVAs. You can just extract those automatically and put them here in this field on the left. So I'm going to use one data set that somebody already did this. So if I go here on the bottom, I'm going to use elderly priming. So this is another form of priming. And here we have Daniel Lakens, one of the prominent people in the science reform, in the open science movement. He already extracted all the things from elderly priming. So if we go back here to the top, you can see which article he extracted, what he extracted, and what the p-value is. And now if we have all of these extracted automatically, we can run some analysis on this. So for example, if we go here, first you can check, are the p-values correct? And this is exactly what StatCheck does. You can upload some PDFs and see whether the p-values make sense, or maybe there's some problem in there. So if you push that field, you can see that it analyzes everything, and in some of those it flags something that we might need to look at. Maybe they reported a two-tail, but actually it's a one-tail. Maybe they got it wrong and it's a completely different p-value. It just flags all kinds of things. So before you submit your thesis, I really recommend run this through StatCheck or take the literature before a study and just upload this and to see whether the PDFs actually have p-values that make sense. But this is like a very, very simple tool. Another thing that you can do is you can run a meta-analysis. Now, what's interesting about this, we're not going to go into how to examine this and what this looks like. But generally, I would say that if you look at this very nice figure over here, you can see that you have an effect of 0. So there's no effect whatsoever, as a triangle. And this is the white triangle. And then there's another triangle, and this is for effect that was found. And here in the priming, the effect that was found is about 0.5, and that is a different triangle. So all the findings should fall under one of the triangles, and sometimes they should fall under both triangles. But most of the findings should fall under this triangle, the gray triangle compared to the white triangle. If most of them fall under the white triangle, the likelihood that this is not a real effect. Now, what you can see here is a very curious thing. Generally, these should be distributed as a triangle. They should be all over the place if this is a reflection of reality. But what you can see is that all the studies fall under the gray triangle, but everything that overlaps with the white triangle is not there. What this means is that this is an indication of publication bias, because if the literature was a reflection of reality, we would have had a lot of dots here as well. But this means that every time we try to submit a paper that had a p-value higher than 0.05, we said, no, it's not interesting because it's not supported. So this is how we know that there's indication for publication bias. So we can use a meta-analysis in order to see whether there's publication bias or not. And we have all kinds of different tests for this. You can see very strong indication for publication bias, very strong indication for publication bias, and so forth. Another thing that we have is a p-curve. Now, p-curve is a very important thing in order to see the distribution of p-values. So the green one that you see over here is what p-values should look like. So most of the p-values should be very, very close to 0. Then less should be 0.01, then less 0.02, then less 0.03, and the least should be 0.05. What's happening in the priming literature? 44% are just below 0.05. There's not that much that is close to 0. And this means that it's very likely that people are just pushing their p-values, doing all kinds of things, like questionable research practices, in order to get their p-value to be just below 0.05. So now we can analyze an entire literature in order to look at this. In addition, you've got some metrics in order to tell you whether this is has any evidential value. It does not. If it has some evidential value, is it inadequate? Definitely. The priming literature has a big problem. It's not adequate. Studies lack evidential value and were intensely hacked. There is evidence showing that elderly priming literature was severely p-hacked with questionable research practices, trying to push it down lower than 0.05. Is this clear? Any questions about this? So now you have Shiny apps and tools in order to allow you to investigate a literature before you embark on a study to see how credible is it or not. We didn't have these tools a decade ago. Let's see how much time I have. I don't have a lot of time, so I need to wrap this up. I'm just going to tell you, people are asking, how do I know that people are doing questionable research practices? We just ask them. And this is self-report, so they admit this. We get very close to 100% when we ask people, are people doing this around you? 100% failing to report all the dependent measures, just like the chocolate study, all the way to falsifying data. Falsifying data, 9%. Unbelievable. So this was in 2012. Since then, we've been running this again and again, and we keep finding these kinds of things again and again. latest poll in the Netherlands, which is supposed to be the most open science supportive place, 4.3 to 4.2 people falsifying the data. And here we have an aggregation of all the questionable research practices. You can see the rates, 40, 50%, 20, 30%. We have very close to 60, 70%, 40, 50%. I wish we did this here in Hong Kong in order for us to understand. But across all these different studies where we just ask people, we don't have any implicit measures. Are you doing this? People are doing questionable research practices. So this is a big problem. We need to address this. But I want to end on a positive note. Now we know that these things happen, and we have ways of addressing these things. And here in this course, we're going to find the way to for us to assess things and then to figure out what is more credible and what is less credible. And there is a way of getting back on track. So my overall assessment of this whole thing is that we need of assessment, of reflection, and improvement. And it's very important that we teach students how to improve on these things. So a lot of things came out in the last decade. Now it's not just me or the open science advocates or the science reform movement saying this. Now UNESCO is saying it. So UNESCO is doing in 2022. They came out with a pledge. Have we heard anything about this here in Hong Kong? We haven't. Have we done anything about this at HPU? We haven't. How about the NASA and all the people in the US? The year of the open science, 2023. Have we heard about this? We haven't. I don't know why. So the rest of the world is doing a lot of things in order to increase credibility and look at open science. But we here in Hong Kong region are very behind. There was a conference actually at HKU looking at principles for open science. And actually they came out with a statement that a lot of people from around the world and a lot of universities actually signed. Who didn't sign the HKU Hong Kong Principle Pledge? HKU did not sign the HKU Pledge, which is very, very weird. But all of us are saying, all these people, all these conferences are saying that we need more and more of this. But the way to address all of these things is just doing more open science. And we're talking about very simple things, open methods, open data, open access, open peer review, open educational resources. So everything that I've ever done in my teaching, all of my videos, everything that the students ever do, everything is open because we want to learn together as a community. This is why open science is so important. And of course, open source. So Jamovi in R Markdown and not SPSS that belongs to IBM and nobody can operate. So it's better for everybody. We're going to learn a lot about why it's better for everybody. And finally, and this is the takeaway that I want you to leave with here. And this is thanks to Chris Chambers. And Chris Chambers has really changed everything that I do. So all of the research that I do follows a lot of these principles. From the book that he wrote in 2015 up until now, everything that I do tries to be a registered report with pre-registration, with open science, everything shared. So what is the status quo research? Stuff that we look at right now that has closed peer review, closed data, closed code. How much should this inform our policy? This should not inform our policy. This should not have a TED Talk. This should not have a book. How do we move up closer to the green? If you start sharing, if you share your data and materials, it's a little bit better because then other people can validate it. How do we get even closer? If we do something called a pre-registration. So we do a plan in advance that is public and timestamped that we upload to a public website before we collect the data. So we're going to learn how to do this, and this is how we do stuff. And then finally, a registered report. And this is very important. We're going to talk about this a lot. This is the solution to a lot of the problems that we talked about today. So at the end, hopefully in a decade or two, I don't know how long it will take HQ to catch up with it, but at the end, we're going to need a lot more registered reports, and we're going to have a meta-analysis that doesn't have any publication bias, that doesn't have any of these issues. So the rest of the world is already headed in this direction. I really hope that Hong Kong and HKU will follow with this. So we've been doing a lot of things at HKU. I'm going to teach you all these tools. We have tutorials on this. We're going to keep coming back to this. But we've done things with scientific evidence. We have things about how to code credibility. What are the different factors? We have a guide for you, effect size guide that I did with the TAs and the HKU students. So over the years, after doing this for 6 years, we have a lot of ways to help you assess what research you should do. And then when you see research, what is it that should inform your decisions and what is it that you do in your life? So last semester, we did stuff on happiness. How do we know what helps our happiness? This semester, we're going to do stuff on pro-social behavior, altruism. How do people help one another? What is that we can do in order to have impact on the world? And we need to do this according to the best scientific practices of what is credible, high open science, things that we can really rely on, things that we can all work together in order to implement this and have a real impact on the world. So this is just a teaser. Hopefully you got something out of this. It will help you think about these things. In the following weeks, we're going to talk about social psychology in specific. So we all heard about Milgram, Stanford prison experiment, bystander effect, all these things, all these classics that we learn about. Are they credible or not? What happens when we put them into the pitch checker? What happens if we go back and we look at the evidence? Is it credible or not credible? I think you'll have some surprising findings. So I look forward to discussing all these things with you. Think about this. Come back next week and we'll have an interesting discussion. See you next week.